and welcome to episode number 6 of CS350 Online. I'm your host, as always, Leslie Ested, and in today's episode, we are actually going to continue our discussion of synchronization. We are going to look at locks, and in particular, how to implement locks that block, but we are also going to have some time to talk about semaphores and maybe even some time to talk about condition variables. Just a couple notes before we get started. First off, if you are reading the textbook, and please understand, it's not actually required, but it is good extra reading if you want to expand your knowledge. Relevant reading would be things like semaphores and CVs today. And if you're working on assignment 1, please note that we've changed the deadline. A student pointed out to me on Piazza that we wouldn't actually finish covering the material for assignment 1 until like 2 or 3 days before it was due. And that's absolutely not fair to you. So I changed the deadline to, I think it's like June 11th or something. It's a Friday. So that will give you more like 10 days to actually work through things. And if you need any pthreads help, of course, Stack Overflow, and there's many, many libraries online that you can actually look at to, what is pthreads? How do I use it? But the one request that we have is, under no circumstances may you use the join command. We want you to use the different synchronization primitives to actually mimic that behavior. And that's just experience. I mean, I know join is an important and easy to use function, but we want you to get some experience actually using the synchronization primitives. The other thing that, I think I've lost my train of thought here. So a couple other things I want to mention is we will not be running Valgrind on your code. So if pthreads leaves a little extra memory lying around, don't worry about it. Now, don't be horrible with memory. Please do free anything you actually allocate. But again, we are not actually running Valgrind, so just keep that in mind. The other thing is, if you wish to write your own testing harnesses for the first question, I highly recommend it. That way you can have more of a deterministic, did I actually count the right number of words, as opposed to, is this in the right ballpark of the right number of words? So that's up to you. And for A1Q1, it's up to you to decide how many threads you want to have the execution take. Some people use 2 threads, some people use many, many, many threads. And it's really up to you to decide how do you think is best to balance the work of managing the threads with the work that the threads are actually going to be doing. So that's kind of a fun task to do. All right, so our OS of the day today is called DTSS, and DTSS was released in 1964, and this ran on a GE200 series machine. And if you're like, GE, isn't that the maker of my thermostat? Yeah. See, back in the day, there were a lot of different companies that actually made mainframe computers. So another one you'll actually see is Honeywell. Honeywell, yes, another thermostat maker. They actually did make mainframe computers back in the day. And in fact, if you've ever heard the term honeypot, that actually stems from the Honeywell machines. Anyways, this ran on a GE200, and this is a product of Dartmouth College. Now, this one came right close to CTSS. And the big difference between these two is that while CTSS was demonstrating the feasibility of time sharing, they only did so with 4 users. And what DTSS's goal was, we want to show that time sharing is actually feasible on a large scale. So this was the first successful large-scale time sharing system. And by large scale, they had this kind of goal. And a lot of research that people do ends up, published in papers, put in a book, sits on a shelf, may not be used for 20 or 30 years, if at all. They didn't want to create an operating system that was used just to demonstrate large-scale time sharing, which is in itself important. They actually wanted to put some effort in to make an operating system that would be used by lots of people. So they had the goal of trying to make it so everybody, or at least as many people as feasibly possible at the Dartmouth School, would actually end up using this operating system. And what's interesting is by 1968, so in only 4 years, they had 80% of the Dartmouth students actually using DTSS operating system. Now, what's interesting about that even more so is you might think, oh, well, this must be some big technical school, except no, I mean, it's like people in history were using it. People in other departments were also being encouraged to use the computer for something, anything. So when they say large scale, they really do mean large scale. Now, when you're thinking about this, you're probably like, so does this mean that every operation was instantaneous? No, you're looking more at like, they didn't want any operation or any response to take more than 10 seconds. Keep in mind that this is 1964, and the idea of computing is still very, very new to most people. Nobody has a computer in their home at this point. So being able to use a computer is still such a foreign idea. But they still wanted people to have the idea that, they have their own computer and things were running very quickly. So the maximum response time was 10 seconds. And that's actually pretty good, I feel, for 1964. Because certainly sometimes even today it can take quite a while for, VLC to respond. Maybe not 10 seconds, but it sure feels like it. All right. So some other things that DTSS brought to the table are things like the first IDE, so that's Integrated Design Environment. And that's something many of you, I'm sure, have used at some point in your life as an IDE. And I mean, I'm not going to lie, I have used IDEs before. I used Delphi back in high school, and then I guess I've used Visual Studio a little bit and Xcode. I don't like them. I'll stick to VI, but they had an IDE. And one of the cool things about their IDE was that they could actually, so if they typed lines of code, it could be automatically inserted into the program and compiled and executed like right away. So it was a very rapid design environment. So that's kind of cool. So yeah, that's DTSS. And the other kind of funky thing about this is it actually remained operation until the end of 1999. So this operating system has been in operation for a very, very long time. All right. So where did we leave off last class? So in our last class, we were looking at the lock primitive. I always scroll the wrong direction. I'm sorry about that. So we have these critical sections. And a critical section is a region of code where a variable, so something like the global variable total, may be read or written by multiple threads at the same time. And we call it a critical section because it's very critical how threads are executed through that region of code. Most of the time when we have a critical section, what we really want to enforce is mutual exclusion, which means we only want one thread able to be in the critical section at any given time. Because if you remember, if you have more than one thread, then the problem we actually come with is this idea of a race condition. And we saw the race condition, we showed you how it worked, where we were having, depending on the order of thread execution, so when do the context switches actually happen, you get a completely different output. And it was because if there are multiple threads reading and writing the same variable at the same time, and you have no control over when context switches happen, then what you end up with is sometimes one thread, it's almost as if it never runs. So you end up with the wrong values in memory. And we also saw that these race conditions can cause runtime errors like segmentation faults, and they can even cause memory leaks. So these race conditions are when the output of your program is dependent on the thread execution order. And this is because of critical sections in our code where we want to enforce mutual exclusion. So only one thread can read or write this variable at a time. And the mechanism we introduced in order to solve that problem was a locking door mechanism, just like you would have in a bathroom. A bathroom has a door that locks so that you can go in and you have mutual exclusion on the room for however long you want it. And we showed you an interesting way of doing that, which was to have a Boolean variable that is the lock. And the idea is, so if the lock is true, then that means that the door is not open. So the door is shut. You can't enter the critical section. The lock has already been acquired. And once the lock turns false, then you can actually acquire the lock and enter the critical section. But in our initial implementation of a lock, what we discovered is that it in itself has a race condition and multiple people get in. And while there are algorithms that can solve this problem, purely in C, they're not very efficient or general in their purpose. So if we want to have something that's appropriate for being in the body of an operating system's kernel, then we need to actually rely on hardware test and set operations to do that for us. And we looked at exchange, which is the x86's atomic swap operation. And then we looked at ARM and MIPS, which use a 2-instruction barrier to check a value, and then if it's changed, know that it's not safe. And if it hasn't changed, then it is safe to update the value. And we're going to continue by just reviewing another way to think about this in just a minute. The question on Twitch is it possible to use timestamps to detect race conditions? Could we just abort the request if there are conflicts? So, I mean, I'm not entirely certain what you're referring to by timestamps to detect race conditions. I don't know how we would use that. I'm not saying it's not possible, but then we're also making the assumption, if we're using a timestamp, that 2 accesses to the same piece of memory aren't happening at the exact same time, which is entirely possible, especially on a multi-core system. So if you have a multi-core system, it's entirely possible that 2 cores, one will try to read from memory and one will try to write to memory at the same time. That is possible. And if the timestamps for both of those are the same, then how would we resolve that conflict? So that's... I'm not saying we couldn't devise a system to make that work. I'm just saying that there's a lot of architectural and interesting details involved there. Also, as another student has pointed out on Twitch, if you have 2,000 threads, I don't think that will be efficient. No, definitely. Anytime you're involving things like timestamps, you are going to introduce some inefficiencies because you're involving the clock, and then you've got to do a bunch of checks. And that's one of the interesting things about synchronization is scalability. And if you have, you can get this thing called resource contention. And the idea is you have like one resource, and if you have thousands of threads trying to access that one resource, you have mega contention for the same resource, and that's really going to mess up your performance. And I mean, it's not to say that that the timestamp problem would be particularly bad, because even something like using a spin lock or a lock is going to be bad for that. Interesting details. Right. All right, so what I want to do now is I would like to review this load, link, and store conditional, but kind of addressing what they do in a slightly different way. So I'm going to open up OneNote, and I somewhat charged up my tablet, so it should be good to go for today, which is nice. There we go. You know, I usually use lined paper in this tool, but I'm really finding I like the graph paper is so much easier to use. And I've really got to fix my pen too. My pen keeps falling apart. All right, so what we've got is we're going to kind of draw what's happening with load, link, and store conditional as kind of like a decision tree, which might seem a little weird, but hopefully it will help you visualize what's going on a bit better. So what we've got at the top is we're going to have our load linked instruction. And what's going to happen here is we're going to set some temp variable x equal to the value at the address. So this is our root. It's our root. Okay. Now, the value at x can be one of two things. It could be true, or x could be equal to false. Now keep in mind that load link doesn't actually look at what the value is because it doesn't care. All it's doing is getting the value at the address at that point in time. If x is true, that means the lock is taken. And then what we're going to do is in our store conditional operation, and this is actually going to be a few lines of the tree here, what happens is we are going to check, is x equal to the value at the address? So that's our question. And if that is true, then we are going to set the value at the address to true. This is a success for store conditional. Store conditional sets the value at the address if the value at the address has not changed since the load link. So in this case, where x is true at the load linked and x is equal to true still, so x is still equal to the value at address, then we have a success and we're going to set the value at the address. Of course, we're setting the value from true to true, so it doesn't do anything. We are going to return x. And what ends up happening is we keep spinning. No lock. It's not available. So these two operations here are kind of our store conditional. And then this stuff down here, this is our test and set operation, which is a C function. Now, if the value at the address has changed, so x is no longer equal to the value at the address, that doesn't mean the value at the address is false, by the way. It just means the value is not true. So the value is not 1 anymore. So if the value is not 1, it could be like -5. It could be 352. We're not going to make any assumptions. And you might be like, well, I'm only going to be setting the lock value to true and false. Sure, but maybe there's a bug in your code and it accidentally gets set to 352. So we're not going to do that. So this results in a failure of the SC operation because the value has changed, therefore we can't set the value. And we're going to return true because we want to keep spinning. We didn't get the lock. Lock is not available, or at least in this case, the value of the lock is unknown. And we are going to not make any assumptions. We only take the lock if we absolutely know for certain what the state of the lock is. And in this particular path here, we don't know what the state of the lock is. So we're not going to assume it's safe to take. Now, in the case where the lock is available, in the store conditional operation, again, we're going to, check is the value of the address still equal to x, and if it is, and that means that it's still false, that means that we set the lock to true, and we get a success. And we return x. Well, x is false in this case, so stop spinning, and you own the lock. But if the value of the lock has changed, then store conditional fails. Failure. And we return true. And that's going to cause us to keep spinning. And we don't get the lock. So there's kind of a pictorial way to see your way through how load link and store conditional operate. The only path of these 4 paths that result in you getting the lock is the one I'm going to highlight right now. That's the only path. So comment on Twitch is, so in summary, it takes advantage of the atomicity of write operations and slips true into the lock. It feels the same for ARM and x86 as well. So yeah, one of the things we are making the assumption of is that only one write to memory can happen at a time. And that's true. You can't have multiple writes to memory at the same time. So your computer typically has one memory controller, and it can typically only really handle like one write at a time. So you wouldn't actually be able to have multiple cores writing to the same address at the same time. It's not to say an architecture won't be developed where that's not possible, but it's just current architectures, if you have a memory write, only one write can happen to an address at a time. So we are assuming that. All right. So there we go. That is our other way of looking at load, link, and store conditional. So what I want to do now, just make sure I get my mouse on the right screen, is let's continue our discussion of looking at the different kinds of lock structures. So we briefly talked about this last class. This is a spin lock. So the kind of lock we have been more focusing on implementing is the spin lock. And the reason why it's called spin is that because there is a mechanism in it that is going to loop and repeatedly ask if the lock is available until you can actually acquire the lock. Now, obviously, spinning is a waste of CPU time because you're effectively using cycles of the CPU, but you're not actually doing anything useful. You're not making any progress. But they actually call this a busy wait. And because busy waiting, we want to actually minimize spinning. So some architectures and operating systems actually have mechanisms that they use to reduce spinning. And OS 161 uses one of these mechanisms to reduce spinning. And that is that when you acquire a spin lock, we disable interrupts on that CPU. And what that means is that for the spin lock, it becomes effectively owned by a CPU instead of a thread. And the reason that's true is because since interrupts are disabled, preemption cannot happen on that CPU, which means no other thread may run on that CPU until the spin lock is released. And when the spin lock is released, interrupts get turned back on. Now, obviously, this is going to cause some issues. What this means is that if you have a spin lock that is acquired, then you have disabled interrupts on a CPU for a period of time. The longer you own that spin lock for, the more interrupts you might be ignoring and missing. And that can be bad because you might be missing key presses, you might be missing network packets arrive. There's all kinds of different things that you might miss. So when we have a spin lock, whether you have a spin lock that actually spins or a spin lock that is disabling interrupts to reduce spinning, you don't want to own it for a very long period of time. You want to use spin locks for the absolute bare minimum of operations. And then you want to use more sophisticated primitives that block instead of spin or disable interrupts for larger operations. Now, this does not prevent spinning completely, by the way, because if you have multiple CPUs and you only disable interrupts on one CPU, then threads running on the other CPU, of course, could actually try to acquire that spin lock and they would spin because they'd be waiting. So that's an interesting thing. All right. By the way, spin locks are already implemented for you in OS 161, so this is not something you're going to need to implement. That being said, it is valuable to at least take a look at the implementation, just kind of get a feel for what they're doing. Now, I showed you last class very briefly the inline assembly. I don't want to walk through that because I'm not expecting you to know anything about it. We do not do any inline assembly in this course whatsoever, and I will not ask you what this means, promise. Now, what we actually want is we want a more generic synchronization primitive. I want something that gives me mutual exclusion, but when the thing isn't available, when the lock isn't available, instead of spinning in a loop, repeatedly asking, wouldn't it be nice if it went to sleep? I mean, this is what would happen ideally. You show up to the bathroom, you see that the door is locked, you knock once just to make sure it's actually locked. And when the person says, hey, go away, you fall asleep. Okay, maybe don't fall asleep on the DC floor. That's probably gross. But when the person leaves the bathroom, i.e. releases the lock, they'll tap you on the shoulder and say, hey, the lock state has changed. Why don't you try again? Wouldn't that be better? No, why would that be better though? That would be better because nobody's spinning. Nobody is sitting there knocking on the door, repeatedly asking, is it available? It is available. It is available. They're waiting for the owner of the lock to release the lock, to change the state, to let you know that the state has changed. And so you're going to go from asleep, which means you're not using CPU time, which means some other thread can use that CPU time. So you go from that, then you wake up, and then you can try to get the lock again. That's better. That's what we want. We call that a lock that blocks. You fall asleep when the lock is not available. But in order to implement that, we're going to need some tools. Now, first off, I do want to tell you, so all the spin lock tools, they are all implemented for you already, but the lock is not implemented. And this is something that you're going to have to implement as the first thing you do for assignment 2. This actually used to be on assignment 1, but we've pushed it to assignment 2 so you could get experience with P threads and, like real threading and stuff. So what I will tell you about the lock API inside of OS 161 is all of these functions actually exist already, except I don't recall if lock do I hold exists already, but they're empty. And your responsibility is to fill them in with all the correct bits and bobs. So how are we going to have a lock that blocks as opposed to a lock that spins? What we're going to need is some kind of space for the thread to wait. The thread can't wait in the ready pool because the ready pool of threads is where threads that are ready to execute are going to be placed so that when there is a context switch, we can grab any one of them and we know they will be ready to execute instructions. So threads that are waiting for an event to happen can't be in the ready pool. They need a separate space to wait. So the question on Twitch here is, what will happen to the program if its thread sleeps? Well, then the program is not executing. The program is asleep. It's not executing any instructions. And what we need is a place for that program to actually live while it is waiting to be woken. And we call these wait queues or wait channels. And the idea is it's a queue where threads can be placed. Remember that in an operating system kernel, a thread is just a structure. We can place the thread structure into the wait queue, and then when the thread that owns the lock releases the lock, it can go to the wait queue and move one of the threads from waiting to ready. And that means we're taking the thread structure from the wait queue and putting it into the ready queue, which means that it could be scheduled to run at any time. So we're going to take it from this temporary holding place and put it back into the ready pool. Now here's the question that you have. How many of these wait queues do you actually have in total? Do you have one master wait queue where everything lives when it needs to wait? So we've got, let's suppose you are playing like Unreal Tournament. It's one of my favorite games. Not Unreal 2, not Unreal 3. I mean Unreal 1 from 1999. If you're playing Unreal Tournament, let's suppose it is waiting for you to actually move. So push a key. So that program needs to wait for you to push a key before it can actually do anything. So let's suppose you're at a menu screen or something. And then let's suppose you have another program that's waiting for a lock to become available. So the program's thread, the thread that is waiting for that lock to become available, will be in that same queue. But then here's the problem with having one shared waiting queue. When one of those events happens, let's say I push a key on my keyboard, or I move my mouse, then I actually have to go through and search the entire wait queue to find the specific program that was waiting on that specific event. That doesn't make sense, because these events could happen hundreds of times a second. So realistically speaking, we don't want to have one shared wait queue. What we want to have is a separate wait queue for everything we could possibly be waiting on. So if I have a lock that blocks, that lock is going to have its own wait queue. And it's only going to hold the threads that are specifically waiting for that specific lock to be available. because that way, when the lock is released and I go to the wait queue to wake a thread who is waiting on that lock, I don't have to check to say, hey thread, what are you waiting for? Because I know already this is the wait queue for this resource, and therefore everybody in this wait queue is waiting on this specific resource. So I don't have to check. So in reality, your operating system actually could have hundreds or thousands or tens of thousands of separate wait queues, each one for a different resource. Now, these wait queues are called wait channels in OS 161, and they are also already implemented for you. And there are several functions in the API. The first one is called wchan sleep. This is the function that is going to take a thread and add it to the wait queue. It is also going to cause a context switch, because if you are putting a thread into a wait queue, that means that you are not going to be running or executing that thread anymore. So we have to perform a context switch, so it will call thread yield if appropriate. Now, there's a question on Twitch which will hopefully be answered in the next two API functions, and that is, do we have to wake every thread in the wait queue or just one? That's your choice, actually. There are two functions for waking threads. There is wchan wake all, which is going to take every thread in the wait channel and move all of them into the ready pool, so it wakes everybody up. Or you can choose just to wake one thread up. And sometimes it is appropriate to use one of these functions, and sometimes it's appropriate to use the other. For example, if we were implementing a lock, since a lock can only be owned by a single thread, then when the lock becomes available, why would you wake thousands of threads if only one of them would ever be successful at getting it? So it makes sense to use wake one in a lock. However, there are other resources, other synchronization primitives, where we may let 100 threads in the door. So maybe it makes more sense to do wake all in that case. wchan is wait channel for those asking on Twitch. So how do you add a thread to the wait channel? You're going to use the wchan sleep function. That is going to add you to the wait channel and cause a context switch to move thread execution to some other thread that is actually able to execute instructions. Now there's one final thing. The wait channel is a shared queue. That means multiple threads can be accessing it at the same time. And so it needs to have atomic functions. Wake all and wake one are already atomic. That is, they have already been protected by a spin lock internally. They are perfectly safe. However, due to the behavior of sleep, sleep can unlock the channel, but it can't lock it. Because if sleep was able to lock it, then we couldn't actually implement locks properly. And we'll see that behavior in just a minute. So we have a lock function for our wait channel that will let us lock the wait channel before we call sleep. And it's really critical that you call lock before you call sleep. All right, and you'll see some more about that later. So just a review of the thread states. You've got ready for threads that actually want to execute instructions right now. That is, they are not waiting on anything. You've got running threads, which are actually executing instructions on the CPU right now. And then you've got block threads, which are any threads that are sitting on a wait channel waiting for a resource to become available. So we've got these three separate states of threads. Okay. Now, this is, and I know the next slide says semaphores, but I actually don't want to go to the next slide just yet. What I would like to do is actually talk about how does one actually implement a lock. Now, I know this is assignment 1, or assignment 2, question 1, implement locks for us, but we always actually go over the implementation in class in pseudocode. And there's a reason for this. The reason is if you get it wrong, nothing in your assignments will work. Like really, nothing will work. You have to have locks implemented correctly. If you don't implement them correctly, then, as I said, nothing works. Like literally, nothing works. So question on Twitch is, where are the weight channels actually stored? So the weight channel will become, so for a lock, for example, a lock structure will actually contain a weight channel. And the lock structures are a part of the, they're going to be stored in the kernel. So let's talk about what should you put in the structure of a lock. I don't want to write with a highlighter, that's weird. So, and this pseudocode, by the way, is already posted on Piazza for anyone who wants to follow along. So we have this lock structure. And if you look at the lock structure, it already contains a name. And that's really just for debugging purposes. It's not really useful for anything else. What else should it contain? Well, we need to know, for example, if the lock is held or not. And we also need to keep track of the owner of the lock. We don't want that to be a Boolean, though. That would be silly. Why do we need to keep track of the owner of the lock? Well, here's a question for you. If you're in the washroom in DC, you own that washroom stall for a moment. Do you want somebody else to be able to reach their hand over the door and unlock it? Should just any old person be able to unlock the door? Or should only the current owner of the bathroom be able to unlock it? So if you want to make sure that the lock is only released by its owner, then you need to keep track of who the owner is. Now, spin locks were owned by CPUs because they disabled interrupts, but locks aren't going to do that. So locks will be owned by a thread. So we're going to keep track of the owner of the thread. Some really good spelling. So it will be a pointer to a thread structure, because thread names are not guaranteed to be unique, but the address of a thread structure is guaranteed to be unique. So that is the best way to actually identify a thread. So we've got the name of the lock for debugging purposes. We've got whether or not the lock is held. We've kept track of the owner. What about a place for the threads that are waiting for the lock? So we're going to need a wait channel. And I like to usually just short form this to WC because I don't like writing that much. Do we need anything else? Actually, we do. Because we still need an atomic test and set operation. And in order to protect our atomic test and set, I don't want to go down to assembly code directly, but I can use my friend the spin lock to offer us mutual exclusion for our atomic test and set. So we'll have a spin lock called spin. And again, this is just pseudocode. Okay, so let's look at acquire. What are we going to have in acquire? So I'm going to leave some space, and then we'll see if this works. I'm going to short form a lot of these in the interest of time. So we've got spin acquire and my lock, spin lock. And so now that I have mutual exclusion, I can do my atomic test and set of the lock value. So while the lock is held, I'm going to do some stuff. Remember that we need to lock the wait channel before we go asleep on it. Oy, bad spelling. And then after we exit this loop, we know that the lock is available because we're going to spin, W-chan spin, that's not what I wanted. I wanted sleep here. I know that when I leave the while loop, this actually means that the lock is available. So now I can actually set the lock held, and I can set the owner. Cur thread, by the way, is a global variable that is a pointer to the current executing thread's structure. And then spin release. Now, question I have is, does this work? Nope, doesn't work. There are a large number of problems with this implementation that I've actually given you. It's close, but it's not quite right. So I'm going to use a different color to fill in the bits. First off, when you enter the acquire function, how do you know that the lock is even initialized yet? So two things we need to check. We're going to use these k-asserts to make sure, a k-assert, by the way, is a kernel assertion, that the lock is not null. Because if the lock is null, you're going to have a bad time. There's another k-assertion we should do. And that is, don't try to acquire a lock that you already own. Because you will go to sleep on your own lock, and since you're the only one who can wake you up, but you're asleep, that's never going to happen. So, you want to assert that you do not own this lock. Now, that's not the only thing that's wrong with this particular piece of code. In this particular piece of code, I acquired the spin lock so that I can check the value of held with mutual exclusion. Because remember that the locks fields are actually shared variables, so many threads could be trying to read and write them at the same time. So they need to be protected, and we're using a spin lock to protect it because we don't want to go down to assembly, and because it's just easy to do this way. So the problem is, right now, I own the spin lock, and then I go to sleep on the wait channel while I own the spin lock, which means that interrupts are technically disabled on this CPU, and we're going to have a pretty big problem. We can't fall asleep owning the spin lock, excuse me, because what ends up happening is then anyone else who tries to acquire this lock is just going to sit there spinning, trying to acquire the spin lock, which is stupid. And I mean, well, they'd have to be on a different CPU to do it, and everybody else would just be out of luck. So we actually need to release the spin lock before we go to sleep. But the question is, do you release it before you lock the wait channel or after you lock the wait channel? And the answer might surprise you. It's after you lock the wait channel. All right, now this should not be a spin here. This should be the wait channel, of course. Now, why do you have to release the spin lock after you lock the wait channel? Here's the problem that would happen if you did it in the other order. If you do it in the opposite order, then what's going to happen is you're going to end up with the situation where a thread is releasing the lock at the same time as you trying to go to sleep on the lock, and you will end up going to sleep on a lock that is technically available. So to prevent that particular condition from happening, we have to lock the wait channel to prevent the thread that is releasing the lock from waking anybody up until you've actually had a chance to fall asleep. That way you won't fall asleep on a resource that's available, because if you do fall asleep on a resource that's available, no one can wake you up. So we have to lock the wait channel to prevent anyone from touching the wait channel while you're falling asleep on it. So and that is actually why lock has to be outside of sleep, but you don't have to unlock outside of sleep because it does that for you. Now, after you have slept and you wake back up down here. Here's the problem. When you wake up, you go into the ready pool. You don't immediately go from waiting to running. You're going to go into the ready pool, and there's no guarantee that you will be the next thread that executes, which means even though you woke up because the lock became available, it's entirely plausible that another thread managed to acquire the lock out from underneath the view. So, when you wake up, you need to double check to make sure that the variable is still, or the lock is still available. And in order to check if the lock is available, you have to do that with mutual exclusion. So we need to reacquire the spin lock here. Okay. So when you leave this while loop, it will be because the lock is available. You will still own the spin lock, which means you can safely set held, you can safely set owner, and then you can finally release the spin lock. Now, it might seem we own a spin lock for a really large period of time, but we actually don't. You only own the spin lock to execute that operation, this operation, and this operation. You don't own the spin lock at any other point in time. Well, I guess you own it here as well. That's it. Those are the only 4 instructions where you actually are going to own the spin lock for, and they don't happen that often. They're very fast. So that is the lock acquire implementation. What about release? What does it look like? Well, release is actually very simple. Should really glue my pen back together. There's this little piece, I guess, that goes around the buttons, and I don't know why it broke off, but it did. Anyways, probably my kids throwing it around or something. All right, so let's look at the release function. Release, as I said, is much easier. And the first thing that we're going to do in release, again, is you need to have some K assertions. And I'm not going to tell you what they all are here. Obviously, we don't want the lock to be null, but there's one other thing. We don't want to own the lock. We want to guarantee that we own the lock we are releasing. So make sure you own this lock before you permit this to actually go. Then, since we are going to be reading and changing the spin lock's global variables, we are going to need to acquire that spin lock for the lock itself, so that we can test and change those variables. Well, we're not testing, so we can change those variables with mutual exclusion. So, and what we're going to do inside is we are going to set the lock held to false because we are releasing the lock. We are going to set the owner to null because it has no more owner. And then, of course, the ever important, we need to wake somebody up. And we are going to call wake 1. And then we are done. All done. That's it. So spin lock lock release, is actually a fairly simple function. All right. And again, this pseudocode is already posted to Piazza, so if you can't read my handwriting, and it is kind of hard, I know, you can just see the typed up answers there. Now, again, you might be like, why are we owning this spin lock again? We own the spin lock because we need to have mutual exclusion to change these shared variables here. And if I don't have mutual exclusion when I want to change those variables there, then I'm going to end with up with a race condition in my lock implementation, and that would be bad. So now we have a lock, and that's it. All right. So for those of you who may need a little extra help, if you go onto Piazza, of course, and you go down to extra sample problems and lecture content, there is a guide for locks, which you can read through if you want. And that might give you some more insight into that. And then again, as I said, the pseudocode for acquire is posted here. And you can use that if you want. There's one thing I will tell you. And the thing I will tell you is this is not the simplest implementation. If you look very carefully, one of these variables can actually be done away with altogether. But I won't tell you which one. So that's kind of on you to try to figure out, can you improve this implementation a little bit? The question on Twitch is, if it's release, then you own the lock. Is that another kind of mutual exclusion? Well, I mean, you own the lock, but other threads could still be trying to check whether the lock is owned or not, which means the lock isn't protecting its internal variables. The lock is protecting something in your code. So the spin lock that is in the lock is used to provide mutual exclusion to the lock's fields. So no, it's not a different kind of, it's just, we need something to give mutual exclusion to the lock fields, and then the lock itself is used to give mutual exclusion to something else. Okay. So you can improve upon this implementation a little bit. I'll let you figure out how to do that exactly. The other thing I want to say is, if you're struggling with this, or if you want to be really lazy, this is totally permitted, by the way. You will notice that the semaphore implementation is almost identical. If you want to copy and paste the semaphore implementation into each of these functions and then just make the few changes, you can totally do that, because the semaphore code is provided to you, and if you want to just copy and paste it as a starting point, you are more than welcome to. In fact, for lock create and lock destroy, I absolutely recommend copying sem create and sem destroy into those, because it's a really good example of how to make it work. So up to you. You can use the code if you want. So for the question on Twitch, what's a semaphore? Hold on just a second, because we're going to talk about that now. Of course, it helps if I open the right tool. I don't think anybody wants to read about my camera movements. There we go. There's the right one. All right. So what is this magical thing called a semaphore that we say you should steal the code from and modify? Well, a semaphore is another type of synchronization primitive, and it's personally my favorite one because it's so flexible in what you can represent with it and what you can do with it. So here's kind of the idea where a semaphore comes from. Think back to a time where you actually had to go to a physical classroom. A classroom has a set number of seats. Those seats are resources. Okay? So a lot of classrooms in MC have 90 chairs. So they usually assign 90 students to the room. Now, for various reasons, sometimes more people show up and sometimes less people show up. So here's what happens. If there's only 90 seats in the room, then if you show up at the room and you see a free seat, you can enter the room and take a seat. You can take a resource, which is the seat. If you, however, show up to the room and all of the seats are taken, then you have to wait for someone to get up to use the washroom before you steal their chair. How do we synchronize that behavior? Because what we don't want to happen is there's 90 resources and we let 110 people trying to take it. That doesn't work. There's only 90 things available, so I can only let 90 threads, you being the threads, into the room to take a seat. Well, this is what a semaphore can be used to synchronize. So semaphores, instead of having the ability to just have one resource, they can have any number of resources. And we can keep track of how many threads have taken resources and how many threads have given back those resources. So we know when all the resources are taken, the thread has to fall asleep outside the room in MC to wait for one of those resources to become available. So a semaphore is something that keeps track of how many resources are available. And I like them because they can be used in very interesting ways. So first off, a couple weird notes about semaphores. When you think of getting a resource, you think of, I wish to acquire a resource. And when you are done with the resource, you release the resource. So it would be nice if semaphores were acquired and released, but they're not. The gentleman who invented the semaphore was a Dutch fellow, and he liked trains a lot, apparently. And so he named the acquire and released functions after his favorite train functions. So to acquire a semaphore, you P it. And to release the semaphore, you V it. Yes, you're going to get that very, very confused. it's easy to forget which one is which. But when we talk about semaphores, we P and V them, not acquire and release. P is the acquire, V is the release. So we're going to P and V them. Now what happens when you P a semaphore is it's going to check if any resources are available. If there is a resource available, then it will let you through, and it will consume a resource by decrementing the semaphore's internal counter. If, however, there are no resources available, then what's going to happen, and that is because the counter is 0, then you will go to sleep. Just like on the lock, you go to sleep if there's no resource. The V function is going to increment the number of resources that are available, which means incrementing the semaphore's private counter, and then waking up a thread that might be waiting on the semaphore. So P to acquire and V to release. Sheldon did not invent semaphores. It was somebody by the name of Dijkstra. But let's be fair. I mean, he likes trains. Sheldon likes trains. Trains are awesome. I like trains. All right. So, what kinds of semaphores are there? So there's there's lots of different implementations of semaphores. But with the very simple implementation of, I want to say, the classic semaphore that's given in OS 161, there's actually some really cool behaviors you can do with it. Like, really cool. For example, we have this semaphore called a binary semaphore. And again, this is not a different implementation. This is the same implementation, just used in a different way. So a binary semaphore is a semaphore that has a single resource. When you actually create a semaphore structure, you tell it how many resources it has initially. I'll show you in a minute. So if you create a binary semaphore, then you tell it has one resource initially. And then you just have to treat it like a lock. So a binary semaphore behaves like a lock. So you P to acquire the lock and you V to release the lock. However, there's a couple big differences. Semaphores don't keep track of ownership. So even though you can use a semaphore like a lock, nobody checks to make sure that you're the owner when you release it, because semaphores have no concept of ownership. And you can kind of think of it this way. If somebody steals your laptop, do you care more about who stole it, or do you care more that the laptop gets returned? I don't know about you, but if somebody stole my laptop, I'd care more that I got the laptop back than who actually did it. So semaphores, yeah, they don't keep track of who owns their resources. So that's one thing to keep in mind. Here's another quirky thing. Semaphores will let you call V as many times as you want, because a counting semaphore, which is the next kind of semaphore use, is a semaphore with an arbitrary number of resources. And here's an example of how a counting semaphore might work. Let's suppose you are a bakery. And I love cupcakes. So let's suppose you're making cupcakes. When you get to the bake shop in the morning, there are no cupcakes on the shelf. So the counter is 0. And any customers that arrive before you've produced any cupcakes have to wait for the cupcakes. So you start your semaphore with an internal count of 0. And then as you bake the cupcakes in the early morning hours, you are going to call V to, increment the counter and make those cupcakes available for the customers who are waiting. So a counting semaphore is a semaphore with an arbitrary number of resources, and it can grow and it can shrink according to how the resources are actually growing and shrinking. So that's kind of an interesting one. You can actually have a semaphore start with no resources. Now you might be thinking to yourself, you could just solve all these problems with things like the binary semaphore being able to call V many times if you just set like a maximum. But they don't do that. Semaphores have one internal counter that just keeps track of how many resources are available right now. All right, there's a question on Twitch about what does P and V stand for. I do not speak this language, so I'm not going to attempt at all to pronounce these words, because that would be very bad if I did. P, let's get a proper pen. P is for this word. I'm just looking up the spelling here. Which apparently this means passing. again, I don't speak this language, so I don't really know. And V, and this is a word I have no idea how to say this. Oops, I've spelled it wrong. VRJIGAV. That apparently means release, but I don't know. Again, I don't speak this language, so I don't want to try to say these words or give you a definite meaning for them. But that is what P and the V stand for. Okay? So for the record, so in OS 161, we do use P and V, and that is the standard API for a semaphore, but some things like Java have decided, wow, that's really bad style, because nobody knows what P and V actually mean. So they've actually changed the API functions to be something that's, meaningful. Yeah. If Dijkstra had been taking CS135 when he invented semaphores, he would have gotten 0 for style, because number one, these are single letter function names. And number two, the letters don't even have, nobody could read that. All right. So binary semaphore behaves like a lock, but is different from a lock in that it doesn't keep track of ownership. And technically speaking, you can call V as many times as you want, which would break it from being, it wouldn't be a binary semaphore anymore. So you have to use it as a lock, but very carefully. So counting semaphore is a semaphore that has some arbitrary number of resources, even 0, because you might have to wait for the resources to be produced, like a bake shop. Someone on Twitch is saying C# also has semaphores. Semaphores are in like everything. Semaphores and locks are like the basic synchronization primitives. They exist in many, many languages. Another use of a semaphore is called the barrier semaphore. And this is our join function in OS 161. So I'm going to open up a terminal. Yes, I know it looks like Python code, and I may not like Python too much, but I am using Python code right now. Because there's some things Python is good at that other languages aren't, and that is natural language processing and machine learning. Python's great for that. And right now I am sifting through the dialogue of 201,000 films. So yeah, I need Python for that. All right, anyways. So we are going to go into the kernel of OS 161. Let's check where I am. Now, if you go into the test, no, that's not, sync probs directory. Now, the old assignment one was locks, condition variable implementations, and then you had to implement a traffic simulation. And if you've ever been on Reddit, the Waterloo Reddit, it was always on Reddit, like people commenting about the traffic simulation. I got rid of that last term, actually, because I felt like while it was a valuable synchronization problem, I would rather you get some experience with real-world synchronization than putting a traffic light in an operating system kernel, which makes no sense at all. So anyways, let's look at it anyways, because this is a prime example of where we're actually going to see the barrier semaphore being used. So if you go in here and you open up traffic.c, I think it's traffic.c, you will see at the very top, there is a semaphore called simulation wait. And simulation wait, when it's actually created, is created with initially 0 resources. The whole point of the simulation wait semaphore is to be used as a barrier. We are going to P this semaphore once for every thread that we create. And only when all of the threads that we create have completed will the thread that called P on that semaphore that many times be able to continue. So we are going to P the simulation wait semaphore some number of times right here. So once for each thread we created for the simulation. And then each thread of the simulation, the very last thing they do is they V it. So as each thread completes, they V the semaphore to let the other thread know I have completed. And then the idea is, since we want to gather statistics from all of the threads we created, and we want to gather those statistics together to print out a final result before we move on, we are going to have to wait for all of those threads to finish. So every thread has to V. So we have to P it num thread times, and each thread will V it once. And then we only do our statistic generation after all of the threads have completed. This is a barrier semaphore use. Again, it is not a separate implementation. These are all the same implementations. They're just different ways we are using the semaphore. This behavior here is effectively what pthread join does. So pthread join, you call join on a specific thread ID, and what it's going to let you do is it's going to wait, cause the calling thread to block until that thread completes. And that's exactly what we're doing with this barrier semaphore here. We are forcing the calling thread to block until those threads have completed. Pretty neat, right? So it's a barrier semaphore. We're using the semaphore as a barrier. We cannot continue execution until the other threads have completed. Oh, so for those of you asking about what is this cleanup state stuff, so this is the traffic simulation problem, which is the old assignment one, which you're not doing any part of this anymore. But the idea is cleanup state was probably freeing a bunch of stuff. So freeing the semaphores, freeing any of the other structures that we actually had. So it's just like a cleanup. And obviously you don't want to free the semaphore until all the threads that use the semaphore have actually completed. Now, if you actually look through some of the other code in OS 161, so if we go into the test directory and you look at thread test, you'll actually see barrier semaphores being used in here as well. So, for example, loud thread V's a semaphore at the very end. It's V'ing a barrier semaphore. So this is a mechanism we use in OS 161 to wait for threads to complete, because we don't have a join function. So this is why I'm telling you, for assignment 1, where you're using pthreads, yes, the join function exists, and we are aware of that. But we would like you to get some experience simulating that behavior with either locks or semaphores or condition variables. Use something else to get that behavior. Do not use join. Okay? It's too easy. All right. So looking at the time here, one last thing I want to show you is just how you would use mutual exclusion for a semaphore. So here is the code from before. I have created a binary semaphore. So again, it's the same implementation. It's just I'm setting its resource and count to be 1. And then I'm going to make sure that how I use that semaphore is exactly the same way how I would use a lock. So before I enter the critical section, I P the semaphore, and when I leave it, I V it. And if I always do this, it will be as if I have a lock, except of course that if somebody makes a mistake and actually V's it too many times, it wouldn't be a lock anymore. And we have no concept of ownership. So this is... But if you're careful, it's fine. And one of the reasons why I like to use semaphores is because they're very versatile in this way. So is a semaphore a replacement of a lock? The question on Twitch. No. So there's places where we should use locks. They're more appropriate. But there's some places where we want mutual exclusion, but a lock isn't appropriate. And we will actually see that place when we talk about devices and device drivers in the last few weeks of the course. And the reason why we like to use binary semaphores in device drivers is because we want mutual exclusion on the hardware. But the problem is that the thread that initiated contact with the device isn't usually the thread that's going to handle the device being completed. And so if it's two different threads that are talking to the device or dealing with the device's interrupts, if we're using a lock, it's not that it's impossible, it's just that it's a lot of extra work and the binary semaphore's faster. So we do tend to use binary semaphores for devices instead. Another question on Twitch is, if two threads P at the same time, would it be broken? No, because the implementation of P looks almost identical to the implementation of lock acquire. It's actually in your notes here. So this is something, unfortunately, I was hoping we would get to today, but we won't. This is actually the pseudocode, just the stripped down pseudocode of the Semaphores P function. Wait a minute, doesn't that, I mean, I've taken out the assertions and a few other details, but hey, wait a minute, doesn't that look like the lock acquire we just did? So no, P and V are atomic. That is that they have full mutual exclusion. So you can't have two threads P to semaphore at the same time. So no breaking there. So this is actually why we recommend, if you taking a look at the semaphore implementation, is because it's very, very similar to the lock implementation. You can see here the major difference, however, is that instead of setting a held variable, we are dealing with a counter instead. So that's all. Okay, so I'm going to end that here for today, and what we're going to do in our next episode is we are going to talk a little bit more detail about why these two functions have to be in this specific order in the lock and semaphore implementation. We are also going to look at the classic synchronization problem known as producers and consumers, because it's one of the classic places where you see semaphores. And then we will dive deep into the condition variables as well. We'll talk about how to implement them, how to simulate them, and how to use them in various ways. So that will be our next episode. So if you're following along with the episode guide, note it's a rough guide because sometimes there's lots of questions, which, by the way, I like that you guys are asking so many questions. That's really, really great. But that does affect the schedule a little bit, and sometimes I talk faster and sometimes I talk slower, you know. Anyways, so next episode, we will finish our discussion of semaphores. We'll do the producers consumers problem, and we will dive into our CVs. So one last question on Twitch, though. In general, do we tend to use spin locks to protect fields for other data structures? Depends. I mean, if you're looking at a lot of basic stuff in the kernel, like really simple stuff, yes, spin locks tend to be used a lot in the kernel of an operating system to protect global variables and various things. And that's usually the case when those global variables are simple things like counters. But we also tend to do that before the memory systems are fully booted in an operating system, because locks require us to use malloc, whereas, or kmalloc, but spin locks don't. So for things early in the boot of an operating system, it's spin locks all the way. And then for really simple things in a kernel, you'll see spin locks. But anything more complicated, we want to move away from spin locks because of the interrupt disabling and the spinning. We don't like that. So yeah, in the kernel, they do get used for a bit though. All right, so we will see you, I guess today is Thursday, so we'll see you next week. I hope you have a wonderful weekend and do something fun, okay?